So in this unit, we're going to start looking at bonding and how molecules are actually put together. But to do that, we need to talk a little bit about some of the background information goes into how these things go together. First thing we want to talk about is talking about ground and excited states of electrons and describe the transitions between them. We're going to talk a little bit about Schrödinger's equation and define known orbital. It's where electrons are actually residing, and then contrast the particle and wave nature of an electron. Electron transitions are what give us the colors. So we can identify elements like with flame tests. Flame test is a great way to identify what element we have. We can take the compound, we can take I've seen it happen where someone just dumps like table salt right on the flame and the flame grows a bright like yellowish orange color. Or salt substitute is potassium chloride, same thing. We pour it on a flame and it burns purple. And so sometimes we'll take an unknown compound, an unknown salt specifically. So a salt again is a cation anion combination where the cation is not H+, the anion is not hydroxide. And we can dissolve it in water, and then we can burn that solution and see what color it turns. And what color it turns gives us an idea of what elements are in that compound. That's how fireworks work as well. Different colors of fireworks come from different electrons being excited from different elements. So the colors of these transitions tell us a lot about the composition of the species that's involved. Niels Bohr came up with, there's a lot of people that came up with the construction of the atom, yes, but Niels Bohr model of the atom actually made this concept of the transition of electrons from different energy states more concrete for us to understand. What we found was that energy must be added to move an electron away from the nucleus to a higher excited state. Energy is released when an electron falls closer to the nucleus to its lower energy ground state. Perfect example in the real world like this is looking at the northern lights. You know, everyone knows about the northern lights or the aurora borealis, and it's really, really pretty, and we always see this like green color, and sometimes we see other colors in there. The colors we're seeing are from electron transitions of an element, most commonly oxygen. The green we see from the green color that's most commonly seen for the northern lights is from oxygen. It's from a transition of the electrons. Electron is excited and a photon is released for a specific amount of energy correlating to what energy that atom actually absorbed. So what we see here is like if an electron makes a transition from n equals 3 to n equals 2 state, what does this mean? So what I mean by that, if an electron goes from here, sorry, I should actually write that for 3. Electron goes from here and it transitions down to the n equals 2 state here. It's kind of what's showing here, okay? That means that this electron is losing energy. In order to go from the third energy level to the second energy level, the electron had to lose energy. It does this by emitting a photon of light with precisely the amount of energy it needs to lose. If an energy transitions from a lower state to a higher state, what does this mean? If I go from, say, n equals 2 up to n equals 5, in order to do that, the electron has to gain energy within that range. And so a photon of light is absorbed with precisely the amount of energy required to reach the higher energy state. Energy must be added to move an electron away from the nucleus to a higher energy excited state. Energy is released when an electron falls closer to the nucleus to a lower energy ground state. And when these transitions happen, especially the transitions from higher energy to lower energy state, it corresponds to different colors of what we see as the rainbow. But we can identify what the elements are and what's being gained and lost in the system due to those colors coming through. Again, one of nature's most powerful driving forces is the movement towards states of lower energy. I know I've said that in class before, I'll say it again. The two driving forces in chemistry is lower the energy of the system and create disorder. So we've got this Heisenberg uncertainty principle. The Heisenberg uncertainty principle. So Niels Bohr initially suggested electrons exist in orbits, and quantum mechanics comes along and treats electrons a little bit differently. Quantum mechanics says that an electron has both wave-like and particle-like properties. What does that mean? It means that an electron can behave like a wave, but also like a particle. The moment we treat an electron like a wave, it behaves like a particle. The moment we treat an electron like a particle, it behaves like a wave. But it can behave as both. The Heisenberg uncertainty principle says it's impossible to know both the position and the momentum of a particle simultaneously. If we can determine the position of the particle, the problem is electrons are so small. They're very, 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 very small. And so the moment we can determine the position of an electron, we have disturbed its momentum. So we have disrupted the momentum of the electron. The moment we can determine the momentum of the electron, we've disturbed its position because it's so small. So mathematically, this is the equation. But the consequence of all of this is we have no way of measuring an extremely small object's location without disturbing it and affecting its velocity. If we do measure it, we're going to affect it. Electron will either act like a wave or a particle, but not both at once. So the Heisenberg uncertainty principle, we cannot assign fixed paths for electrons, meaning we can't say the electron only resides here. The most we can hope to know is the probability of finding an electron in a given region of space. Since an electron has wave-like properties, quantum mechanics is also called wave mechanics. Quantum mechanics is a mathematical description of an electron, so it gives us Schrödinger's equation here. But basically, the whole point behind this is that we can describe a region in space where we believe the electron is residing. We can't tell you exactly where it's at because we're going to affect the electron itself then, but we can give you a most probable location of an electron, and that's solved mathematically. So Schrödinger's equation, we treat electrons as a wave function. There are 4 quantum numbers that tell us the most probable location of an electron. It's like the address of the electron, where we get the state, the city, the street number, the house number. It's telling us where it thinks the electron resides. The wave function is psi. Psi squared is probability density, the probability of finding an electron at a particular point in space. The equation, the Schrödinger's equation, can only be solved exactly for hydrogen. However, when adjustments are made for factors such as electron repulsion, electron-electron repulsion atoms with more than one electron, we get useful approximate solutions. And there's also node in the function where there's zero probability, where the probability of finding an electron drops to 0. Because of this, though, we can actually determine, we know that electrons can have s orbitals. We know we have p orbitals. Those aren't drawn very well. It looks like kind of like a bow tie or a sideways figure 8 or an infinity symbol. We can have our d orbitals, which look like this. There's 4 that look like that. There's 1 that looks like this. And I cannot draw the f's. But the electrons will reside in this area. So for like an s orbital, the electron resides somewhere within here. P orbital, we've got 2 sides to it with a node in between. The node is here. D orbital, the node is here. F orbital, or C, this is another d orbital. There's 4 that look like this with different positions. 1 that looks like this. But we can see the electron resides within here. We just don't know exactly where.